Okay. Again, sorry about forgetting that. There they are. Would you mind throwing me that green towel behind you there? Thank you. All right, any questions over anything before we get started? Did you all have a good weekend? No, terrible.
Yeah, it was bad.
Bad weekend. I'm sorry to hear that. All right, well, we are going to continue with where we left off, which was factoring, but really the solving of the equations. So did anybody have any issues solving, wait, did we do? Yeah, solving the quadratic equations? Any problems you want me to go over? I'll get us warmed up by doing one of these. How about 9x squared plus 18x plus 8 equals 0. All right, so we are looking at a quadratic equation. We know that because we have x squared in here. Equal sign makes it an equation. So whenever we have quadratic equations, the standard procedure is to move everything to one side and get 0, right? Okay, so we've done that. We also put in descending order, so highest power of x first, then bring the x down, then the constant by itself. Now what? GCF. So do you have a greatest common factor? Is there a number that goes into 9, 18, and 8? No. And there's not x's in all of them, so no GCF. All right, so now what? AC method, right? Because there's 3 terms. So the way that I've done it in class is do this thing. And I'm going to multiply 9 times 8, which is 72. And then the number here, 18. And then you have to come up with these 2 numbers that multiply to be 72 and add up to be 18. 6 and 12. So that part might take you a little while. You just do that work on the side, but you get those 2 numbers. And then we rewrite this as 9x squared, and then we're going to rewrite the 18x using these 2 numbers. Since they were both positive, I'll put plus 6x and plus 12x, then plus 8, and then equals 0. And now we have 4 terms, and then we do grouping. So what can I pull out of the first 2 terms here? 3x, which would leave me with 3x plus 2. And I believe you all like the matching where we just wrote 3x plus 2 and then equals 0, and then tried to figure out if there's a number that I could use here. 4? Plus 4. And that's it. So by the feel I'm getting here, either you're all tired and it's Monday, or you understand this and we're all good to go. What is it? Both? Both? Okay. So I'm going to write 3x plus 2, and then 3x plus 4 equals 0. And then what do I do with this? Said each one of those equal to 0, right? Both factors equal to 0. So we call each of these factors. So 3x plus 2 equals 0, and then 3x plus 4 equals 0. And x is negative 2/3, and x is negative 4/3. So I would assume that you could get from here to here by just moving things around, dividing through. All right, so that's what we ended with last time. So today we're going to do a couple of more things involving this, solving quadratic equations, but we're going to take a look at something else before we continue. All right, so we're still doing solving quadratic equations, but we just need to do a quick little recap of radicals. Or if we want to say square roots. All we're going to deal with here are square roots in this class. Radicals is a more general term. All right, so there's some notation here. Hopefully we've all seen this before. That symbol, that's the square root symbol. And if I write in here square root of, let's say, 4, then what would this be? 2, right? Why? Because 2 squared equals 4. So when you say the square root of 4, you're saying what number times itself gives you 4? Well, 2. 2 times itself gives you 4. And I can do this for all sorts of things, right? We have very common ones that we should all kind of be familiar with. 121, that's a perfect square. It's 11, right? And then we have less common ones that are harder to come up with. What's that? Root 32? Yeah, so what we'd like to do with this is if it's not a perfect square, right? If it's not a perfect square like these are, then we try and break up the 32 and see if when we break it up, one of its factors is a perfect square. So can you think of a number, 2 numbers that multiply to be 32 other than 32 and 1?
4 and 8.
What is it? 4 and 8? Can anyone think of something else?
16 and 2.
16 and 2 would have worked. Anything else? I think that's it, right? 32 and 1, but we said don't consider that. So those seem like the only 2 that we can come up with. Do you agree? So when you look at these, do either one of these a perfect square? Yeah. Yes, 4 is a perfect square, isn't it? Or either one of these a perfect square? Yeah, 16. So in both of these cases, we could do the following. We could rewrite this as root 4 times root 8. That's using a property of radicals that allows you to split them up. As long as this is multiplication, you can do this. Just beware, caution. That was supposed to be a star. If you have this, you cannot do this, all right? You are not allowed to split up a radical with addition inside. No go, all right? But if it's multiplication, you can. And I'm going to move this one down a little bit. What would this be? What's square root of 4? Well, 2. And the square root of 8? Well, that's not a perfect square. So then you'd have to break the 8 down. Can you think of something that multiplies to be 8? 4 and 2 again, right? And then you split this one up into 2 radicals. Understand what I'm doing? What's the square root of 4? 2 again. So I have 2 times the square root of 2. How about square root of 2? Can you think of anything that splits up? The only thing it breaks up to be is what? 2 and 1, right? So we have gone all the way. This number right here is prime. It cannot be broken down. It's not a perfect square. So we're done. We have to do 2 times 2, which is 4. We get 4 root 2. Understand? Now, I said that you could do it this way, or you could have done the root 16 times 2. Right? That was also one of the options. And this turns out to be, if you split it up, root 16 times root 2. And what's the square root of 16? 4, and then root 2. And you can't break the root 2 down, so you see you're already here without all this work. So when you have a number like 32, what you want to do is try and split it up into 2 numbers where one of them is a perfect square, right? But the biggest one you can get. Now, even if you don't get the biggest one, you're going to eventually get there. It's just going to take you longer. Let's try something else. Questions? How about root 90? So 90 is not a perfect square, right? Can you split that into two numbers? 9 and 10? Can you think of any others that might be more efficient? I heard 2 and 45, 3 and 30. Can't really think of anything else off the top of my head. 15 and 4? Is that right? 6, sorry. 15 and 6. Of all of these, this is the only one that I see that contains a perfect square in it, right? 9 is 3 squared. So I'm going to go with this one. This is going to be root 9 times root 10, which is 3 root 10. 3 times the square root of 10. And the 10 can't be broken down, right? Because 10 is 2 times 5, and you can't go anywhere with that. Understand what I mean by that? Can't go, okay. Just, they're prime, you're done. Now please be aware that this is a number, right? There is some number that you can square and get 90. And on your calculators, if you take calculator out and you do the square root of 90, you're going to get some answer, right? Go ahead, Mom. What do you got? Or anyone. What's root 90? 9 point something? 9.48. Good enough? Approximately? Okay. And does that make sense that that would be about 9.48? What's 9 times 9? 81, which is smaller than this. And if we round this up to 10, what's 10 times 10? 100, which is bigger than this. So somewhere between 9 and 10, our answer should be in there, right? What's up?
No, it's just the calculator gives out the 3.
Okay, good. So there's a button you can go and turn it into a decimal. It should say like F to D. Let me see. Where is it? Right. Here, hit the green button. And then I believe this one right there, table. Yeah, and hit enter. That didn't do it.
A little arrow button.
Which one?
The second to the bottom one on the right.
Okay, try that
And
one.
the answer of the.
Try that. Oh, there you go. It's the little arrow button next to the number 3, to the right of number 3. And it's different if you're using a different calculator. All right. How about this? What is 6 plus root 63 over 3? Right, order of operations is important here. Remember that this big division bar tells you do everything on top first, right? You have to figure that out before you can divide by 3. So look at that root 63. Let's work on that over here. Can you think of how you could break down root 63? 9 and 7? I like that because 9 is a perfect square. So I can go what, 3 root 7? 3 root 7. So I'm going to rewrite this as 6 plus 3 root 7 over 3. Now, you cannot put these two things together unless you get your calculator out and get a decimal. Okay, that's the only way you could get an actual answer right now, is to put these together, and then after you get that, divide by 3. But we can still do a little bit of simplification. What we can realize is that in the numerator, there's a 6 here and a 3 here, right? I can factor a 3 out, and that would leave me with 2 plus, I'll put 1 root 7, even though I don't need it, over 3. So let's see if that makes sense to you. If you distribute this 3 back through, 3 times 2 would give you 6, right? And then 3 times 1 would give you 3. And remember, we don't, I'm pointing at you, Joshua. Remember, when you're multiplying, you don't go through to both of these, right? So it's either the 1 or the root 7, but not both. So that's why this 3 times this just becomes 3 root 7. Are we clear? Okay, so this 3 and this 3 reduce out, don't they? And you're just left with what was in the parentheses, 2 plus root 7. I don't need the 1 in front. So that's what we call the exact answer. And now what I'm going to do is get the approximate answer. And that you need your calculator for. So go ahead and do 2 plus root 7, and please someone give me the decimal. Four point something? 4.645. Okay, good enough. 4.465. We call this the exact answer because it's the answer with no no errors at all, right? There's no error in this answer. That's exactly the answer. Now, if you want to have a feel for what that number is numerically, like so you could graph it or something, then you need at some point to cut these decimal points off because your calculator keeps going, right? So once we cut it off, we've created error. And so we call it an approximate answer. All right? Any questions? Yes?
Like in the test or whatever, do you want the answer in the approximate form or the exact form?
Good question. I'm going to want the exact form. However, as we progress, you will be doing problems where you will need the approximate form because you'll need to graph these. This is going to wind up at some point being an x-intercept for a parabola. And you need to know where to put that point. And if I tell you, hey, just go to 2 plus root 7, where is that? But if you know it's 4.5, then 4.6, then you know it's what? Somewhere between 4 and 5? It's easier for you to graph that. So you need to be able to do both. Does that answer you? Okay? All right. Yes?
How did you get from 6 plus 3 square root 7 to the third step?
Okay, so look, what if I wrote this down? 6 plus 3x. Can you pull a GCF?
Yes.
GCF would be 3?
Yes.
And you'd write 3, and then you'd write 2 plus what? X, right? And then you distribute that through?
Okay.
You all right with that? This x is that root 7.
Okay.
Now do you see it?
I see that.
Okay.
I didn't know you could do that.
You can. Yep. Yep. All right. What about this? That look familiar? Is that the same problem I just gave you? Close, right? Close. The only difference is that there's a minus instead of a plus, right? So if you were to do this one, you would do maybe the same thing. 6 minus, and then you would write 3 root 7 over 3. So that would be the same, right? Breaking up the root 63 into 2 pieces. Then we could pull the 3 out of the top again. But this time we would have what in this parentheses? 2 minus 1 root 7, right? Over 3. Do y'all see the difference? Just the minus sign, right? That's the only difference. And the 3's cancel, and you get 2 minus root 7. Now that's going to be a different answer, isn't it? This is the exact answer. The approximate answer is what, though? What's 2 minus root 7? Negative 0.645? Very different answer, right? The last one we got was like positive 4.6. This one's negative 0.645. Very different answers by changing that, right? Okay. As we proceed, we're going to get a formula later on called the quadratic formula. It's going to have this symbol in it. I'm just going to restate this problem. Right, this. You're going to see this symbol plus with a minus underneath it. Plus or minus. And all this means is that you have to look at both scenarios. You have to do 6 plus root 63 over 3. That's one answer, right? 6 minus root 63 over 3, that's a different answer. So when you see this expression, 2 solutions, right? That's 2 answers. Okay, just be aware of that. All right. This is going to seem even more off topic, but let me ask you this. What is the square root of 81, or no, you know what? I'm going to do this. Negative 8 squared minus 4 times 2 times negative 5. Now, we did talk about order of operations earlier in the semester. Tell me what you would do first here. Do this parenthesis, exponents. So, like, I can't do anything negative 8, right? Negative 8 can't, negative 8 is negative 8. But exponents, I can square it. So what's negative 8 squared? 64? Positive though, right? That's 64 minus 4 times 2 times negative 5. Okay, what's the next operation that you're going to do? Multiplication. Which one? Okay, so this is where things get really tricky for people. I mean, some people just get it, it's fine, but this is where most people make mistakes. You have negative 4 times 2, right? There's multiplication, and there's multiplication here. You're supposed to go left to right. The problem that most people have is here's what they'll do. Let me just show you. I don't want you to write this down. Here's what people will do. They'll say, what's negative 4 times 2? What's negative 4 times 2?
Negative 8.
Negative 8. So they say, okay, those two become negative 8. But then I have times what? Negative 5, right? What's negative 8 times negative 5? 40. So they put 40 here. But what was sitting out here? 64. So they say 64 times 40. That's the thing I see people do. It happens. Trust me, I've been doing this for a while. All right? So here's the way I suggest that you do this. Have y'all seen this before? I know most of you have. Seen that formula? The quadratic formula? We're about to do that formula in just a second. What I've been doing here is leading you up to that. See that plus or minus? See, we're going to have that in the formula. This right here, this b squared minus 4ac, is this part right here that I'm showing you. So when we are doing this formula later, you are always going to have this minus 4 here. So what I recommend you do when you see this later is ignore the minus sign completely. All right? And just do that. 4 times 2 times negative 5. What's 4 times 2? 8 times negative 5? Negative 40, right? So now uncover this and put down right here what we just said. What was it? Negative 40. Got that? Sorry. Negative 40. I covered up everything. Covered up the minus. I did 4 times 2 times negative 5, got negative 40, right? But what was there? A minus, right? So now you have minus and negative. What does subtracting a negative do? It becomes addition. So this becomes root 64 plus 40, which is root 104. And maybe it goes further. I'm just going to stop there, okay? The idea here is just make sure that we look at this at least once before we proceed. Questions, comments, concerns, complaints? Okay. All right. Now, how about this? What's the square root of 1, everyone? 1, right? What number do you square to get 1? And before I do that, how about this one? What's square root of 0? 0, right? 0 times 0 is 0. So how about this? One. All right. This negative right here is really a negative 1, right? That's what it is. And it's implied multiplication right there. So this is actually, what's that? 1, right? You just told me that was 1. And then times negative 1. So the answer is negative 1. I'm giving you all these things because this is what people get kind of hung up on sometimes. What about this? Yeah, so I hear some people saying imaginary or saying I, right? Okay, you've heard this before? Maybe some of you have. Huh? There can't be a negative under the radical. Why? Why can't you have a negative under the radical? Why is that such a problem? Think about this. What was square root of 4? Go back to this. This was 2, right? Why was it this? Because 2 times 2 is 4, right? The square root of 9 is 3 because 3 times 3 is 9. So when you take the square root of something, you're trying to say something times itself must give you what's under here, right? How can you multiply anything times itself and get negative? You can't, right? It's impossible. If I take a number, it doesn't matter what it is. It's either positive or it's negative, right? If it's positive, then you multiply 2 positives together, you get positive. If I have a negative number, I'm going to multiply it times itself, and that's 2 negatives multiplied to be a positive. So it's impossible to pick a number, multiply it times itself, whether it's positive or negative, and get back a negative number. So this doesn't make a whole lot of sense, does it? But it actually has a value. It's called I. It's called the imaginary unit. The imaginary unit. And I'm going to spare you about 30 minutes of me going off on this, okay? But let me just say this about it. I did most of my graduate work and a lot of my thesis on problems that involved imaginary numbers. And you may look at them as imaginary, kind of like if I told you right now that I have an imaginary friend, right? Sits on my shoulder. Been here the whole semester. Every time I come in, sitting right here, hanging out with me. You would think I'm kind of losing it, right? You would have a little bit of a problem with that? Yes? It's okay. It's okay. They still love you. All right. No, I just have the bad one. I don't have the good one. Okay, so here's the deal. This is a terrible name. Because what happened is in the beginning of mathematics, people were trying to figure this out, and they were basically saying, why? You don't need to figure it out. It's a stupid idea. They called it the imaginary unit. It was almost like, come on, this is like made up math. Later on, a mathematician came along and proved that the square root of negative 1 must have some meaning to it. And it turns out that we developed a whole branch of mathematics out of it called complex analysis, which is based upon the imaginary unit. And I can tell you right now that the square root of 1 is just as real as the number 1 is. It's just as valuable, just as important. Unfortunately, we didn't get to rename it. So everyone at this level, when we teach to you, say imaginary, you don't give it any value, any credit. But trust me, it's very valuable. And I'll give you one example. My brother was, when he was in graduate school, he went to Boston University and did electrical engineering, and then he went to Georgia Tech to do his graduate school. And he called me up with this problem, and he couldn't, he was having some trouble with it. And the problem was very difficult if all you use are numbers that we all use, right? But if you're allowed to use imaginary numbers, the problem became trivial, very easy. And that's a lot of how imaginary numbers are used. It's kind of like putting on a different set of goggles and looking at the world in a different way. And if you do that, sometimes you can filter out all the noise and you can just see the stuff that you want to see. And imaginary numbers allow us to do that. That's it. I kept that under, 7 minutes, I think? That was quick, right? I could keep going. I'm not going to. Whew. All right, hold back. So when you see a root of a negative number, what you're going to do is you're going to put I there, and you're just going to wave your hands at it and say, I don't understand what that means. It's just I, okay? And then later on, you can take a class on imaginary numbers if you'd like. All right, so I'm going to do it this way so you all see what's happening. That's the same, right? Using the property that I can split it up. What's the square root of -1? The imaginary unit I. What's the square root of 4? 2. I times 2, we like to write it 2I, not I times 2. It's multiplication, so it doesn't matter. It's kind of like x times 2 is 2x, same sort of thing. What's negative root -9? Now, there might be a part of you that's sitting there going, well, wait a minute, is he trying to trick us? Because a negative and negative becomes positive, and then this becomes root 9, and root 9 is 3, right? But it's order of operations here. You have to imagine that this root acts like a parenthesis, and you must do what's in it first. So what is root -9? 3i. Everyone agree with that? And then times what? This was like a -1 out here? Negative 3i. All right. Now let's continue solving quadratic equations. There's a special type, a special case where we use a special technique to solve a quadratic equation, but it has to look exactly right to do this. All right? You've got to have basically. Let me write down a specific example first, and then I'll kind of illustrate what it is that makes it special. Is this a quadratic equation? What makes it quadratic? The x squared, right? Is what makes it a quadratic equation because of the equals. What is different from this in the previous problems? It only has 2 terms, right? It's not 3. It's missing the x term, right? We have an x squared term. We have what we consider a constant term, but we're missing the x term. So this is the special case. We're missing the x term. And we just have the squared and the constant. We have x squared term and constant. If you have this situation, then what we will do to solve this is use what's called the square root property, or square root method. It's pretty clear, or pretty clean, I should say. What we're going to do is isolate x squared. You remember when we were doing linear equations? That's what we did. We isolated x on one side by itself. Here we're going to get the x squared term by itself. So I'm going to take the negative 27 and move it to the right side, which would make it positive 27. So I am isolating x squared term. Is it isolated? Yeah, but there's a 3 in front. I don't like the 3. I'd like just x squared. So how do I remove a 3 that's being multiplied? Divide both sides by 3. When I divide both sides by 3, I get x squared equals 9. And then at this point, I do what's called the square root property. I'm going to take the square root on both sides of the equation. So I'm going to take the square root of the left side. And notice I'm writing this on another line. You'll see why in a second. I'm going to take the square root of both sides. When we do this, I know someone's teacher in the past has told them, don't forget, you have to do, when you do square root, you have to do what? Maybe not. Yes? What? Who said it? Plus or minus. Good. You have to do plus or minus. And that is usually explained in the way of just, hey, don't forget it, okay? When you do the square root, don't forget plus or minus. But just think about why you have to include plus or minus. Well, let's get the answer, and then we'll talk about why it has to be that. What's the left side? Square root of x squared. This root and the squared essentially cancel out. You're left with x equals, and then plus or minus 3, because the square root of 9 is 3. So you have two answers here, don't you? 3 and negative 3. The reason why we have to do plus or minus is because if I come in here and tell you, hey, guess what? Some number squared is 9. Then it could be 3, right? 3 times 3. Or it could be negative 3 times negative 3. So there are two possible answers, right? So there they are. Got it? So this whole method right here is called the square root method. Or they refer to it sometimes as the method of square roots. I have a question for you. And this is a little bit of a trick question. Everyone agrees with me that the square root of 9 is 3. Why didn't I do plus or minus here?
Isn't it because it's understood?
It's what?
It's understood.
That's right. It is understood. If someone presents you with a problem, here it is, square root of 9. There are two answers. There are two numbers that you multiply together to get 9. You could do 3 times 3, right? Or you could do negative 3 times negative 3. Either one of them, right? But if somebody's giving you this problem, you will always return to them the positive answer. That's it. The difference between that and this is that this was the original problem presented, and we initiated the square root ourselves. When you initiate a square root on both sides of an equation, when you do that, you must do plus or minus. If you never take the square root, like here we never did, like we didn't just like throw it into the problem, it was there, then you just take that positive answer. And we call that the principal root. All right, let's give you one to work with here. How about 5x squared trying to think of something that's not so nice. So can you use the square root method here? Is it a quadratic equation? Is it missing the x term? Yes. So isolate the x squared. To do that, you'll add 42 to both sides, right? What would the next step be? Divide both sides by 5. Yeah, that's why I gave you this. I wanted to see, like, what do we do now? You know, that's a fraction. It doesn't reduce, right? 5 doesn't go into 42. We could turn it into a decimal, couldn't we? But we're going to try and keep our answer exact. So since this doesn't clean up, right now I'm going to come in square root on both sides. And remember that when I do, I have to add the plus or minus to get the two possible answers, right? And now you look at root 42 over 5 and you say to yourself, is there anything I can do with that? And Caesar said no. That was you, right? Did you say no? That was a hiccup, right?
Yes.
Yes, I know. You could try that, but that doesn't help unless we can break the 42 down to be two things. Do you remember how I did this earlier? I could split 90 up into 9 and 10. Root 9, root 10. So if you inside you can split roots up, put them back together. If you have division, you can split it up and put it back together. Same thing. But the root 42 doesn't clean up. So we were done. We can be done here, or we can put it back into one root like that. Either one of these would be fine. And then if you wanted to get the decimal, the approximate answer, how would you do this? You do 42 divided by 5 first on your calculator. Get that? 8 point something. And then square root.
So you square root 8.4.
Take 8.4 and then take the square root of that, which would be what? Plus or minus, what is it? 2.89. So you should make sure that with your calculator you can get this on your own. What happens on a test if you forget the plus or minus and you just do one of the answers? It's all wrong? I'll give you partial credit. You know, you'll get a lot of credit. Yes?
Okay, so assuming one of these questions is on the test, would you want it in the decimal form or with just plus minus square root?
Well, that's kind of what Caesar asked, right, earlier? I mean, it just depends on the context of the problem. If it was presented like this, I wouldn't mind just the exact answer. Later on, when we're graphing quadratic functions, you will have no choice but to go to the decimal if you're going to have any hope to graph. So later on in the exam, you will have to go all the way to the decimal. But when you're given a problem like this, okay, on a test, I do want to see the work for it. You can't just have the answer. Well, all these calculators have solve features, and you can type in an equation, it'll solve it, and you get the decimal answer, and you're done. Do we have any questions? I always tell my, this is 13-14, right? We have the 14-14 for students who are going on into pre-cal, Cal 1, and they're going to be engineers and computer scientists and all that, right? I always ask them the same thing, you know, like what happens if you forget the plus or minus? Well, in a test, right, you're just going to get some points taken off. But in the real world, bridges fall, planes, wings fall off of planes, bus full of children go off the side of the road. I like to do that because it always gets them to think about it, you know. People remember, you know, if we count pennies, right, in a word problem, that's boring. We count bodies, that's different. Everyone goes, what? We're counting bodies? Like what? You pay attention, right? Same sort of thing. What happens if you forget plus or minus? If you ask any of my 14-14 students, they'll see kids die, all this. You know, they remember it. Y'all must think I'm really morbid. I'm sorry. Okay, are we ready? We are almost ready to start with the quadratics, the quadratic formula. 1:30, we have a few more minutes. These little plus or minus things seem like pretty trivial, but probably before, I don't know, I think most of you were born when this happened, but you know that we have a rover on Mars, right? We have several, okay. Well, before we had rovers there, we actually had to send probes to Mars, just to like go in orbit around and just kind of check it out, take pictures, and so we kind of knew what we were getting into. And one of the first probes that we sent out to Mars was a joint project between the United States and some companies in Great Britain. And we sent the probe out, several $1 million probe, like a $10 million probe, and we lost it. I think most of you were kids when this happened, like little children. Some of us remember. Okay. So they lost the probe, millions of dollars gone. Well, they found out later what the problem was. You had the European engineers working on the project. You had the American engineers working on the project. Guess what they forgot to do?
GPS.
No, this metric system and US system. You know how we were doing conversions in here? Remember that? Convert 100 meters to miles, whatever. Well, the programming in the computer was programmed for both metric and US. It was mixed up. So like a mile here versus a kilometer, that's two different measurements. And so basically, instead of going around and orbiting, it just went straight in and they lost it. So, you know, they were off a little bit, plus or minus, you know, no big deal. It is a big deal. It does matter. There were children. There was a busload of children on the probe. Yes, yes. All right. Quadratic formula. Let me put the formula up here, and we'll take our little break, and then we'll start doing problems, okay? All right, so solving quadratic equations with the Big Daddy quadratic formula. And if this was a 14 class, I would actually derive the formula. I would show you where it comes from. We would extract it, and we would be, wow, that's where it comes from. That's cool. But here, we're just going to give it to you. We're just going to say, here it is. All right, so the quadratic formula is a very important formula. What it does, it says that if you are given any quadratic equation, does not matter, okay? Any quadratic equation that I can ever come up with, it must look like this. I'll put an example next to this. 2x squared minus 5x plus 7 equals 0. That's a quadratic, right? Let me give you another example below this. 4x squared minus 10 equals 0. Here's another quadratic. 5x squared minus 7x equals 0. Those are three quadratic equations, aren't they? But they're different. In this first one, we have three terms, right? Here we have two terms. We're missing the what? X term. So we could actually do that problem using what we did last time, right? This one, we're missing the constant. So I'm going to put a check mark next to this because we know how to do that, right? How would you do this one? How would you do this one? You would, yes, okay, yes, you're ahead of me now. Yes, how would you do this? You would factor GCF, right? If you're missing the constant, won't both of these have an x? And then you pull the x out. And then you just set each of those equal to 0 and you're done. So that's pretty clean if that happens. Understand? This one though, if we have this, our method is to try and do factoring with that little thing, right? And what if it doesn't work? What if we can't come up with these numbers? Well, that's what this is all about. The quadratic formula is a way to get answers to quadratics that we can't find this, we can't complete this thing and do it. Remember I said, if you can't come up with the numbers, that doesn't mean it can't be factored, it just means that you can't come up with those numbers. They're not nice numbers, they might be crazy numbers in here. So what we want to be able to do is solve something like this, and you can do it with this. Notice that the A, B, and the C are just the numbers in front of the x's and then the number by itself. So this is the A is 2, Here B is what? -5, and C is 7. We could say here that A is what? 4, B is, it's not here, so it's 0. And C is -10. Here we would say A is 5, B is -7, and C is 0. So I'm just telling you, for this one, and this one, all of them, you can still use this formula that I'm about to give you. As long as you can identify A, B, and C, you're in business. So if somebody gives you this equation, then the solutions, I'll put the solution /S, meaning you could have one solution, you could have more than one. The solution or solutions are x equals -b plus or minus the square root of b squared minus 4 times a times c, the entire quantity divided by 2 times a. Always. That's pretty nice that we have a formula for that. Isn't that nice? Just curious, if I change this to like a cubic equation where this was like x cubed, x squared, x, and then numbers, do you think that we have an equation for that? What do you think? What does your gut tell you? We do. We do. And it's about 4 or 5 times bigger than that one. It's real ugly. And then what if we have ax to the 4th and like then x cubes, so like a 4th power? Do you think we have a formula for that? Yeah, it's a couple of pages long actually. And then what about for the 5th power? Amazingly, it turns out that it can be proven that there is no formula for 5th and higher. Not that we haven't found it. It's different. If I said, hey, we haven't found it, that's one thing. But I'm saying we've proven it doesn't exist. Totally different statement. So for 5 and higher, you don't get a formula ever. All right, let's take our break. It's 1:38. I will come back. What have we been doing? 10 minutes? Yeah, 1:48 is when so it's 1:38. I'm going to come back at 1:48. You want to come back at 2:15? Is that what you said? Or you want to come back at 12:40 tomorrow? That's what you want to do. All right, take a break.
So, quick question real quick.
Yeah, let me mute.